Happy Friday, everyone.
Howdy.
So today we have a bunch of stuff to get through, and we've already gotten through a bunch of stuff this unit so far. So I wanted to start by giving you an example of sort of a schema that you could use to help bucket all of these things that we're learning throughout the unit. So I want to talk about a summary sheet, a skeleton of a summary sheet, and we'll sort of fill out what we've done so far. And you can continue to fill out the information on this sheet as we proceed for the next couple weeks. And then what you'll end up with is a really nice like one-page summary of the key results that we've learned in this unit. And I'm hopeful that that's going to help you not just as a reference guide for yourself when you take the final, but also as a way of helping see the connections between what we're doing, so it doesn't seem like a bunch of random things that you have to memorize, like a lot of different things. So it's actually just a few main techniques that we're using. The main new content goal for today is to understand our first undecidability proof. So we've talked about a DFA acceptance language and a CFG acceptance language. What we're going to see is that a Turing machine acceptance language, that's a language that's actually undecidable. And so the way that we show that it's undecidable is something that's pretty new. And so that's going to take a while to just sit with that. So I want you to see that as soon as possible. But let's start with the summary sheet. You can come back after class and read this kind of note, which just outlines what section 4.2 looks like. So section 4.2 includes this main proof that we're doing. And so you should definitely understand that main proof. But there's a lot of 4.2 that's kind of more general. It's really interesting, and it might be kind of nice to just skim it, but we're not actually going to be covering a lot of that in class. So this is just kind of an outline of what you don't really need to worry about from section 2. Okay, so we have basically these 9 languages that are going to be the focus of our classification goals for Unit 3. We've talked about acceptance languages, where I say, given a machine of a particular type and a particular input, does that machine accept that input? So we have this for DFAs, we have it for CFGs, and then today we're going to start talking about it for Turing machines. We also have this empty type of language, where I say, given just an encoding of a machine of a particular type, is it the case that that machine doesn't accept any strings? Is it the case that the language of that machine is the empty set? Now, EQ is saying, given a pair of machines of the same type, is it the case that their 2 languages are equal? So these are the 3 formats of languages that you need to be thinking about. And you can go ahead and make a note of the theorems that we've already gone through that are classifying these first 5 languages as decidable languages. So another thing that you can do is see that these results all easily extend to basically like 3 other equivalent types of results, where I can say that the decidability of a DFA, or the A DFA problem, reduces to the regular expression problem, which the book calls AREX, because I can take a DFA and convert it into a regular expression. So if I can take a DFA and convert it into a regular expression, that means that if I had a way of solving a regular expression, I could have a way of solving DFA. So that's not the direction of implication that we want. The direction of implication that we want is, if I instead look at a NFA, I could convert an NFA into a DFA. And because I know that DFAs are decidable, the acceptance problem for DFAs are decidable, that means the acceptance problem for NFAs are decidable. And then we get our third arc in this equivalence cycle, where I say I can always take a regular expression and convert it into an NFA. So these languages, if instead of giving you a machine, a DFA, I give you a non-deterministic version of that or a regular expression, I can decide those languages as well. And similarly, we're saying if we're thinking from the perspective of a CFG, well, I could take a PDA and convert it to a CFG, or I could take a CFG and convert it to a PDA, but CFG will be sort of our core thing that we're studying. So we can kind of put NFAs and regular expressions and PDAs a little bit out of sight for just the goal of classifying these languages as being decidable. Now, I think what's really smart is to try to get in the habit of writing 1 to 2 line summaries of each of these proofs so that those techniques are at the ready for you. So the way I would summarize this first proof of theorem 4.1 that says a DFA is decidable is I would say the Turing machine that shows that it's decidable is a decider that works by simulating D on W. And then you can check whether D ends in an accept state, and if so, you accept. If D doesn't end in an accept state, then you reject. And that's a finite time process, and so that's something that I can actually build a true decider based on. So the basic way that the decider worked for eDFA is we had our Turing machine on the tape, and we decided to do a breadth first search process to mark all of the states reachable from the start state. And then if we reached an accept state, that meant that the language was not empty, or that the language of the DFA was not empty. So the DFA is not in eDFA. And if we did not reach an accept state, then that meant that the language of the DFA was empty. So that DFA is in eDFA. Now, the first time where we really saw a reduction was in showing that EQ-DFA was decidable. And so we can conclude that EQ-DFA is decidable by saying, take an EQ-DFA problem, so this is 2 machines, and convert it into an eDFA problem, and then use the eDFA decider to figure out what your EQ-DFA answer is. So this conversion process, where I take a pair of machines and turn them into one machine that's related, involved constructing the symmetric difference of the 2 machines. And when I take the symmetric difference of the 2 machines, I feed it into the eDFA algorithm. If eDFA says this symmetric difference machine has an empty language, then I know that the original 2 machines are equivalent, and so I'll say yes. So last time we started talking about how these techniques do or don't translate when we start talking about CFGs now. So theorem 4.7 said that a CFG was decidable. And in the book, they talk about deriving a bunch of strings of a certain length and seeing if W is one of those. We gave a different proof in class. The proof that we gave in class said, first convert your grammar to an equivalent Chomsky normal form grammar. And then we could run the CYK algorithm on our Chomsky normal form grammar and whatever string we had that was an input to the ACFG problem. So instead of simulating, there's not really a machine to simulate here, but we have an algorithm that does this parsing problem, so we can use that algorithm that we've already talked about. Now, we did kind of take this emptiness decidability question and take some indication from the DFA case, where we said, let's just see if from the start we can somehow get to an accept state. But with ECFG, we're saying, let's see if from terminal right-hand sides, we can somehow use variables that only generate terminals and eventually find the start variable, because that's going to indicate that somehow there's a way of getting from the start to an all terminal string, and that means that the language is not empty. So I could describe this as mark all the variables reachable from all terminal strings and see if start gets marked. So where we got stuck was EQ-CFG, and we got stuck with EQ-CFG because we looked at this conversion and said, well, with EQ-DFA, we could reduce that to EDFA. Could we somehow reduce EQ-CFG to ECFG, which we do know how to solve? Now, the reason that we weren't able to do this reduction is because the conversion step, where I say take my EQ problem and turn it into an input for an E decider, that conversion step involved doing some processes that are not possible in CFGs, even though they are possible with DFAs. So the symmetric difference can be written as intersections and complements and unions of machines that we already have. Unions are fine for CFGs, but I can't intersect or complement CFGs and be guaranteed that I'm still going to have a CFG. So we don't have a way of classifying this yet. What we're going to focus on today is the result that if I take the language of combining a generic Turing machine, could be a recognizer, not necessarily a decider, combine a machine encoding with an input and ask the question, does this machine accept this input? That is an undecidable problem. Now we're going to start to get a little more nuanced here, and we're actually going to have a result that, although this problem is undecidable, it is recognizable. And we'll also come up with an argument that tells us that if we know it's undecidable and we know that it's recognizable, then it cannot be co-recognizable. So think about what your summary of these three results is going to be as we talk through them. And then at the end of class, you can go ahead and update that. And then next week, we will start to classify the remaining three languages, as well as some additional examples that reinforce those techniques.
Could you remind us what co-recognizable means?
Yeah, good. So actually, let's hold that. We'll get to that today. So the idea of co-recognizable is it's the opposite of recognizable. Recognizable is that you can identify yes answers. Co-recognizable is basically that you can identify no answers. But we'll explore that more fully with those results. So the other thing you should be keeping track of, as well as just these classifications of these languages, are just whatever general results come along that aren't about a particular language, but they're about a technique that you can apply to maybe many of these languages. So you should definitely be up to speed on the definitions of Turing machines, including like what a configuration is, what does it mean to be in the language of the machine. Decidability and recognizability are definitions to go back and just to have top of mind. What we're going to do right now is this additional theorem in 4.2 that we didn't have a chance to cover, or 4.1, which is that context-free implies decidable. So this is 4.9. Today, after we talk about this new undecidability result, we're going to look at a theorem that basically shows how I can combine pieces of information about recognizability and co-recognizability and how that relates to the question of decidability. And then later on, we'll develop some new techniques for doing more complicated classification questions. So any questions about what's on your self-review, self-synthesis summary sheet right now? Cool. Okay, well, let me get myself a little more space here. Come on. My iPad doesn't want to flip. Did it get locked? I don't know why it's not turning. Okay, well, we'll do horizontal all today. Okay, so last time we said theorem 4.7 was the result that A CFG is decidable. That's this guy up here. There's also a theorem 4.9 that we didn't talk about, which is that every CFL is decidable. So this is where being really precise about these definitions comes into play. You can glance at these and say, it's not even clear to me what the difference is between these theorem statements, much less what the difference between the proofs are going to be. So the difference is that ACFG is a particular language. We've defined this as the language that includes encodings of CFGs bundled with inputs that they generate. When I say every CFL is decidable, what that means is give me a language that is recognized by some CFG. So that's what a CFL is. That language is decidable as well. So the picture here is that we have the class of decidable languages. And theorem 4.7 says ACFG lives in this class of decidable languages. Now we also have a class of context-free languages. And these are all of the languages that we studied in Unit 1. So we have like 0 to the n, 1 to the n. We have the number of ones equals the number of zeros, and lots of other things. And so theorem 4.7 says that all of those languages are decidable languages. So understanding how the statement of this corresponds to this result, the statement of theorem 4.9 corresponds to this result, that's important, that you should be able to understand that. So understanding it allows us to set up our proofs in the correct structure that actually proves the thing that we're trying to prove. So we already did theorem 4.7, but just as a reminder, saying that ACFG is decidable is like saying I have to build a Turing machine that decides whether an input that looks like G combined with W is in the language of ACFG, which is the same thing as saying W is in the language of G. Now, in contrast, the proof of theorem 4.9 should say for any particular language L that is a context-free language, show how to build a Turing machine that decides whether W is in the language. So my input on this hand is going to be a W. My input on this hand is going to be a G combined with a W. And I'm going to have a separate Turing machine for each L in the language. Now we can draw, yeah, question?
Do either of these reduce to the other one?
Yes, they do. So let's start with the one that we've already seen and see whether we can reduce the other one to this thing that we already have a result for. So the one that we've already seen is that we know ACFG is decidable. And now because of its inputs, let's write inputs in red. Candidate elements of ACFG are going to be written like a G bundled with a W. So our decider for ACFG, we can just refer back to the place where we have this summarized. We want to convert our G into Chomsky normal form, and then use the Chomsky normal form version of G with W and run that through CYK. So I'll just write that again. Convert G to equivalent Chomsky normal form grammar G prime, run CYK on G prime and W. And then whatever CYK says, I'm going to output a yes or a no. So what my except means is that W is in the language of the grammar that was the input. Now that's the same thing as saying the combined input GW is in ACFG. So my decider is ACFG. What I want to do is figure out whether its input is in its corresponding language. And I'll reject on the other hand. So if I want to set up a Turing machine, specifically a decider, for the language, because I need to show that every context-free language is decidable. So I'm going to show that whatever language L, which is a context-free language, I'm trying to decide, that's the language I'm trying to decide. The input to this problem should be a single W, and I want my accept to correspond to W being in the language. And I want my reject to correspond to W not being in the language. So I'm going to reduce this to my decider for ACFG. And I'm not going to fill out what's in there, but what's in this box is the same as what's in this box. Those are the same boxes. And my reduction has to say, how do I take my input, how do I take my input W and turn it into an input GW, where I can pass that GW in, and a yes to this answer, to this yes answer to this question corresponds to a yes answer to this question. Well, I have a W, I need a G. That G is hard-coded into my machine in the form of L. So I know that any language has some context-free grammar associated with it. I know that any context-free grammar has some Chomsky normal form grammar associated with it. I actually don't even need to convert it to Chomsky normal form because my ACFG decider does that already. So G, where the language of G equals L, is basically hard-coded into this machine. It doesn't depend on the input. The input is just going to be whatever string W I want, but the machine already knows what CFL it's attached to. So I'll just take that hard-coded G bundled with W and pass that into ACFG, and then I can just forward the answers. So ACFG will decide if W is generated by G. If it is, then that means that W is in the language L. Questions about this? It's kind of weird, but basically everything we do from now on is going to be meta like this. So you want to start getting used to it.
So you're saying by definition that G is a grammar of L. Thus,
A grammar of L, yeah.
Thus, by having L, there is a grammar that can use W.
Yep. Yeah,
So can't we just say L taking W?
Right, so L is a language. A language is a set of strings. This guy takes as input a grammar.
And
So if it's
but
expecting a grammar, I can't pass in a set of strings.
okay, so we're saying that G is one of the grammars of L.
Yeah, so G
Of
is some grammar whose language is L.
okay.
Yep. And because I know that L is a CFL, some G exists. So I'm not going to bother myself with figuring out what that G is. I just know that out there, there's a Turing machine that is hard-coded with a grammar that recognizes the language. So I'll take that hard coding and bundle that grammar with whatever W I pass into the machine, then run a CFG, and then I'll be able to figure out whether W is an L. All right. Then our big result for today is theorem 411, which says ATM, which just as a refresher is the language of machines M bundled with W, where M is a Turing machine that accepts W. This guy is undecidable. So this result is kind of going to play the role of pumping lemmas from units 1 and 2. If you recall, in all 3 of these units, anytime we try to show that something is decidable, we build a Turing machine that decides it. If we try to show that something is context-free, we build a CFG that generates it. If we try to show that something is regular, we build a DFA. Now, in units 1 and 2, we said to show something's not regular, I'm going to give you this property of regular languages and show you that it doesn't hold. And I'll do the same thing with context-free languages. Now, there's no concept of pumping when it comes to Turing machines. And that kind of comes from the fact that Turing machines have just so much more flexibility than these simpler machines we worked with, because they don't digest their input from left to right. So they can mess up their input and go back and restore their input and keep going back and forth. There's all sorts of looping that can happen. And we can't really reason about cycles the way we can in the past. But what we can do is the same core thing, which is proof by contradiction. So with pumping lemmas, we fundamentally are saying, assume this thing is regular. Then by the pumping lemma, these things have to be true, but they're not true, so that's a contradiction. So we're going to try to construct a contradiction here that this particular language is decidable. And what we're going to do is we're going to show that if I had a machine, I don't know how it works, but I have some machine, and it outputs accepts or rejects that correspond to whether or not its input is in that language. My goal is going to be to show that this is impossible somehow. My approach is going to be to use it in a reduction. So I'm going to take a machine. I don't want this to be a black box yet. We'll come to black boxes later. So I'm going to design a Turing machine called D. And I'm going to pass it some inputs. And it's going to generate some outputs. And what it's going to do in the inside, this guy is going to be what I draw as a black box. Where I take my machine H, which is allegedly deciding the ATM problem. And if it's deciding the ATM problem, then these are going to be the outputs when I pass in M and W. And so D will do some pre-processing where it decides based on its inputs, what M and W does it want to pass into H. And then it will also do some post-processing to decide how it wants to convert the H outputs to its own outputs. And what we want to say is that somehow the thing that D has to output based on how we've constructed it is going to be a contradiction. So this is just a sketch, a kind of pictorial sketch of the proof. It's pretty high level. So now let's go ahead, and I still don't understand why my laptop or my iPad isn't rotating. Let's try to lock it and lock it and see if that works. There we go. I just forgot about gravity for a minute. Okay, so let's make this more precise. We're going to actually give a proof of theorem 4.11 now. The first step is going to be effectively to assume that this thing exists. So we're assuming this for contradiction. What we want to say is that it's not possible to have any H that does this. So I'm going to make my assumption for contradiction. That my language that I'm trying to prove is undecidable actually is decidable. And if it's decidable, then there exists some Turing decider H that decides the language. So this is why I'm drawing H as a black box, because I have absolutely no idea what H looks like. I just know the way its inputs and outputs behave. So I'm going to build a D that fits this picture by just providing some pseudocode. So I'm going to say D on input M. So now my input for this D is just going to be some machine. M is a Turing machine. I don't have to know for sure that it's a decider. I just know that it's a machine. Step one is my pre-processing step. And what I'm going to do is bundle M with itself so that it looks like this. So this is kind of a weird thing. This guy is a Turing machine encoding. And I'm going to interpret it as a machine. So it's an encoding. It gives me all the rules for a machine. I'm going to say, I'm going to treat this like it's actually a machine. But this guy is like a meta encoding. And instead of treating it as a machine, I'm going to treat this as input. So it's also a TM encoding. this time it's interpreted as a possible input to its own encoding that's being treated as a machine.
So you're inputting a machine into the machine, basically?
I'm allowing H to decide to do that. So what H wants is it wants something to interpret as a machine, and it wants something to interpret as input to a machine. I don't know for sure that H actually plugs W into M, but if it ever does that, then what it's really doing is it's plugging M into itself. So H wants something to interpret as a machine and something to interpret as an input. And so what we're saying is whatever machine we pass into D, tell H to interpret that machine as a machine, and also tell H to interpret that machine as an input to itself.
Sorry. So how does M by itself, how can that be interpreted as an input?
Yeah, so there's an encoding of M, and we're always thinking in terms of binary. So if you write, let's say instead of just Turing machines in general, let's say we're talking about DFAs. So if you create a DFA through JFlap and you save it, that is saved in some particular file format, which you could convert into binary. So that binary thing, that's a bit string. Now that's a bit string that encodes a machine, but if I want, I could take that bit string and just feed it into your machine and see if your machine accepted itself.
I thought that our machines produced just a binary solution, not a string.
So they take in a string,
Yeah.
in a binary string, and they decide whether that string is in the language or not.
Mm-hmm.
So what this would be doing is it would be saying, take your DFA, turn it into binary, and feed that binary string as input into your DFA. And then your DFA can decide whether it accepts that input or not.
So is it similar to like casting in like a programming language, I guess?
What kind of casting?
Just pretty much like you have something and you want to pretty much convert it so it's readable, essentially. Like,
Yeah.
I don't know how to explain it exactly, but it's, I don't know, I guess it kind of seems similar to me.
You could kind of think of encoding as a way to take some object with structure and turn it into a binary string so that if you casted that binary string as Turing machine, then it could be interpreted as a Turing machine. So the idea is here, this is a binary string that can be cast back to Turing machine structure, whereas this is a binary string that could be cast but won't be. It will just be treated as a binary string.
That makes more sense. Yeah, so you're breaking it down to like its principal parts, basically, just like the binary. Yeah, that makes sense.
Yeah, I'm breaking it down into some encoding scheme where I'm like, I'm not going to treat special blocks of zeros and ones as being special. I'm just going to treat them as zeros and ones. So step 2 is the reduction part, where I'm going to say, I don't know how H works, but I am assuming for contradiction that it exists. So if it exists, I can pass any well-formatted input on it. And so I'm going to take these things that I've bundled together. And then I'll just see what H does. Now, my post-processing is actually going to be that I'm going to report the opposite of H's answer. So my machine now looks like if I take my input M, my pre-processing phase is going to say combine M with itself. That's way too small to see. I know that H accepts a machine and an input, but just say that that input is going to be the encoding of the machine. And then if H says, yes, that machine is in the language of the machine, then I'm going to reject. But if H rejects, then I'm going to accept. So in short, what I'm doing is I'm saying step 2 asks H if the machine M accepts itself as input. So something that might accept itself as input would be a C++ compiler written in C++. So a compiler is going to answer a yes/no question. Is this a valid compilable C++ program? Yes or no. So if I write a C++ compiler in C++, it's going to ask for a program as input. So I could feed the compiler into itself, and the compiler should be able to certify itself as a valid C++ program. But the issue is that by playing opposite day in step 3, we're saying that step 3 guarantees that D rejects self-acceptors and accepts non-self-acceptors. So D should reject a well-formed compiler.
Can you go over the definition of what ATM is again?
So ATM is the set of strings that have a common structure, and that structure is that it's an encoding of a Turing machine combined with an input, and it should be an input that is accepted by the machine.
So is it a set? So it's a set of Turing machines that.
It's a set of Turing machines combined with inputs. So if I have a Turing machine that recognizes just strings that are all ones, then encode that machine. If I combine it with 111, the machine combined with 111 is in ATM. That same machine combined with 101 is not in ATM. Also, a machine that accepts all zeros, that M prime combined with 000, that's going to be an ATM.
So ATM contains multiple different Turing machines?
Yes, but all of them are bundled.
I'm just confused about like where like the emphasis of where we're starting from, of like, are we starting with a string and making Turing machines that recognize it, or are we starting with a Turing machine?
Both at once. So ATM says, give me a machine, give me a string. I'm going to tell you whether the machine accepts the string.
Okay. And so when we say ATM is undecidable, we're saying it can't decide if M accepts W?
Yeah, we're saying that there is no generic algorithm that knows how to look at any possible machine and any possible input and determine whether that machine accepts that input.
Isn't that the same as proving that M is undecidable?
Because if M is, because what I have to be able to do is accept all possible M's and all possible W's combined together and figure out whether that M accepts that W. You see a Claire hand raise.
This is a whole new question. So
Okay. Well, let's maybe pause on Taylor's then for a second.
I think I'm understanding it a bit more.
Okay. It takes some marinating. So sometimes when you start, now that we're talking about machines, Turing machines for Turing machines, it seems to get more confusing. In fact, this language, ATM, is no more complicated than ADFA. So I might recommend, now that we're talking about ATM, going back and looking at that language ADFA and making sure that you understand what the elements of that language are. So going back and forth between these two will be really helpful for making sure this sinks in. And also try really hard to understand this during this lecture, but also don't be discouraged if you can't, because this is very much one of these topics that you need to kind of keep looking at with fresh eyes a couple times. So alternate question from Claire.
Do self-acceptors and self-rejectors even exist?
Good. So what we're trying to do ultimately is come up with a contradiction. And so Claire has this intuition that the idea of a self-acceptor or a self-rejector feels like a logical contradiction. And in fact, we are precisely trying to build a logical contradiction. So it feels like it should be impossible to build a logical contradiction. And it is impossible to build a logical contradiction. But if we build a logical contradiction on top of a black box that we don't even know if this black box exists or not, then the existence of this bigger contradiction contradicts the existence of the black box. Contradicting the existence of this black box tells us that there's actually no decider that decides ATM, so ATM is undecidable, which is exactly what we're trying to prove. So let's explore this contradiction. So what happens when we run D on itself? So there are two possibilities. D is a decider. Let me actually, so D is a decider. Let's confirm this. I define my Turing machine like this. And step one is definitely something I can do in finite time. Step two is running on this black box, but if I'm assuming that this black box is a decider, that means it will terminate eventually. Inverting its answer is something I can do. So if H is working properly, then D is a Turing decider. So as a decider, there are two cases for what it can output when I feed it into itself. Case one is that D accepts itself as input. Case two is that D rejects itself when I pass it in as input. So if, in fact, D accepts itself, then what H is going to do is it's going to decide when I bundle D with itself, is it the case that D is in the language of D? So H will decide D is in the language of D, that corresponds to an except. And in step 3, we say that we flip the answer. So D rejects. So it makes no logical sense. There's no logical way that this Turing machine that we've just built can accept itself. Because if it accepts itself, then H is going to accept the bundle, because that's how H is set up. It's set up to figure out whether the second element is in the language of the first element. So if it accepts itself, then H accepts, but then in the very next step, D has to take that accept and turn it into a reject. So that's impossible. It's a contradiction sign. On the flip side, if D decides to reject itself, then H will decide that D is not in the language of D, because that's what it means to be rejected. Then H will reject. And so D will flip that decision and accept. This is also a contradiction. So I'm going to end by saying both cases are impossible. So H can't actually exist, contradicting the decidability of ATM. So let's go ahead and take like a 3-minute break before moving on to the last 10 minutes. I'm going to be here. I'm not going to talk unless you guys have questions, which you're welcome to. You're also just welcome to use this 3-minute break to go to the bathroom or clear your head, however you want.
I'm still struggling to figure out how a Turing machine or any of the machines we've talked about can be converted into a string.
Yeah, okay, so we haven't talked specifically about how a Turing machine could be converted into a string, but we did, I think Friday of last week, maybe Monday of this week, we talked about how you could write a DFA as a string. Do you remember that?
No, I do not.
So we gave an example in coding of a DFA where I said, just list some number of ones based on however many states you have in that machine. Then separate it with a 0 and have q more ones that basically tell you where should your machine go starting on state 1, reading a 0 as an input. And then have q more ones that tell you where you should go if you read 1 as an input. And basically encode delta as just a bunch of 0s and 1s. And then you can also encode the set of final states as 0s and 1s.
Yeah, I totally don't remember this, but I believe you.
Okay. Yeah, I mean, and you don't have to remember the details of this because this is not like a particularly special or smart encoding. This is just some encoding that works. And the takeaway from this, and you can go and you can just, you don't even need to rewatch the lectures. You can just scan the notes for when you see a string like this. The takeaway from this is just that I can develop some way of interpreting a particular sequence of 0s and 1s as all of the information that I need to understand how a particular machine works.
That makes sense to me. I do not see it in my notes that we did that.
It's not.
That makes sense.
doing the encoding is not a skill that I want. That's not a skill that I'm asking you to take. Knowing that such an encoding exists so that you can look at a problem like this and say, what the heck does it mean that I'm going to treat a machine as a string? What it means is you have some encoding scheme. It's complicated.
Yeah.
The computer deals with it. That's it.
I don't know. I don't know if this is the wrong way of thinking about it also, but like I guess something that's helping me right now trying to get through it is like if I imagine like simulating a Turing machine in like a program, it's going to eventually get converted into zeros and ones if you compile it, of course. And
Yep.
imagine taking that compilation of zeros and ones and putting it back into that that machine that you wrote, basically.
Yeah, so that's the idea of feeding a machine into itself, which is critical to this proof. But even more generally, taking a program and just compiling it into zeros and ones. A program is a machine, and a program can be saved in binary. So that's the encoding of the machine.
Yeah, you're kind of doing two, I guess, if you want to do that.
Yep.
Two different running programs with programs.
Mm-hmm. Yeah.
Is the reason that we choose to pass in the encoding of the Turing machine as the input so that we can force recursion to create this contradiction? Like, why didn't we just pick any string, right?
Yeah,
Pick the encoding on purpose.
Yeah, that's actually super insightful to think of this in terms of recursion. And we're not really forcing recursion because we don't know for sure how H works. But if H works by actually running the machine on its input, then we are forcing that recursion. And that infinite recursion is going to block H from being able to eventually decide whether to accept or reject. So this is not necessarily recursive, but the natural way that you would expect H to work would cause recursion in this case, which is why H doesn't work. Does that kind of make sense?
Or more like recursion in the logic rather than like literal recursion.
Yeah. I wouldn't necessarily call it recursion in the logic. I would call it like, I think what's happening is inversion. So because with step 3, we're flipping, then what we're doing is we're taking a yes answer and saying that the yes answer has to be a no answer. And we're taking a no answer and saying the no answer has to be a yes answer.
Yeah.
You might be able to interpret that as recursion. I don't, but I could see that working too.
So is the main point to construct this D that like flips on itself, and we use D with the input M as a template for that?
Yeah, right. So D needs to be described not just for a particular input, but for all inputs. So this description says no matter what machine, bundle it with itself. Now, for some machines, that might be fine. Like for compilers, that's fine. I could take a compiler, bundle it with itself, and say, hey, does this compiler accept itself as a program? There's no logical problem there. That's actually something that can be done. But what's a problem is the special case that we say, well, if D is this program, feed it into itself. And that's where we get this impossibility. So D might work on some inputs, but it doesn't work on all inputs. And so it's not a decider.
And also the reason that we know like the description is D not accepting bracket D or D accepting bracket D, like the fact that we can pass in bracket D is because we can turn a Turing machine into its encoding.
Yeah, exactly. Yep, there's some encoding scheme that allows us to do that. These are really good questions. Okay, so I want to get to one more, I don't know if I want to call it a result or just sort of a thought process. I think I want to call it a result. So if we didn't have this insight, and probably you wouldn't have had this insight without this, this lecture or the book, because this is like a pretty trippy thing to be able to construct on your own. If we didn't have this insight, what we might have tried to do is build something that actually does decide this language. So what we did for DFAs is we said, if you give me a machine and an input, just simulate the machine on the input and see what it outputs. And so that idea is actually Alan Turing's universal machine, depending on exactly how you interpret that universal machine. And it's defined like this. Take a machine U, and if I give it a bundle of an encoding of machine and a string, then I'll run M on W. And if M accepts W, then I will accept MW. And if it doesn't, I will reject. So we just proved that ATM is undecidable, but it kind of looks like this is a machine that decides it. Why is that not the case?
This because in the case that we were describing before, you were saying something along the lines of if M accepts, we then reject, and if M rejects, then we then accepts.
That's a good thought. It's not quite, because we actually have two set up to say acceptance equals acceptance. So there's no flip-flopping that's happening here.
Okay.
Is it because if M never stops running W, then step 1 will never stop?
That's exactly right. So a decider can't have any steps that might get stuck. But M isn't necessarily a decider. M is just a Turing machine. It might be that we get unlucky and we take a Turing recognizer along with an input that it loops forever on. So this guy might loop forever. So U doesn't decide when M loops on W. Now, if W is something that gets affirmatively rejected by the machine, then we know when M rejects W. And we also know when M accepts W. So the language ATM is we want to identify anytime M accepts W. So this acceptance phase says if M accepts W, then step 1 will eventually terminate. And then when we get to step 2, we accept. So what that means is that U is a Turing machine that recognizes ATM. So ATM is recognizable. Remember that a recognizer always outputs yes when the answer is yes, but there's no guarantee about what happens when the answer is no.
So is that when we used co-recognition or whatever that term was earlier?
Yes.
The reject state for that, for basically the same thing?
Yep. So what we're going to show at the beginning of next time is that if ATM were also co-recognizable, Meaning if there existed a Turing machine that identified affirmatively all of the no's, that would contradict the undecidability, because we could combine this recognizer that we know exists with a co-recognizer that may or may not exist. And if the co-recognizer existed, we could run both of those and just take whichever answer we actually get. And that would become a decider.
I see. And then you can also maybe prove that like it's undecidable at that point instead of, or unrecognizable instead of just recognizable.
So it is recognizable. This shows that it is recognizable, but this contradiction shows that it is not co-recognizable. So our results, that we'll summarize this and then go back to the results and make sure that we understand how we have a proof of undecidability. Our universal Turing machine shows that it is recognizable. And having a co-recognizer, along with it being recognizable, would contradict its undecidability. So that's our starting point for Monday. Have a good weekend, you guys.
Thank you.
Thank you.
Thank you.